Good morning, everybody. So welcome in the next day of our summer school. Let me again go briefly through our today's program. We have three presenters today, Antonio and Heiko. Both of them are going to have two presentations, two lectures. Antonio is going to be the first. Then we have today two slots for short presentations of you. And after that, we have a banquet. For that event, we are going into a brewery, which is like 15 minutes going by metro. So later on, we will provide you more information about where to meet, so you can go there with us, meet here just after the presentations, or there is also a possibility to meet directly there. If you would prefer to go to hotel, for example, and come a little bit later, it's no problem. Yeah, some of you also ask me if we have some like more tickets for your spouse or friends if they are here with you. So yes, we have asked there, and still there is a free capacity. So in case you would like to invite also your friends or spouse, it's possible. Just tell me, and I will tell you like about the price of this dinner and beer there. So just come either to me or to my colleagues at the registration desk during coffee break. Hopefully it's everything I wanted to tell you. There was one thing more. Yes, there was one thing more. I have got also a request for some of you that who are not able to participate on Friday's experiments. I don't remember the names, so if you are here, please let me know, maybe immediately, because my colleagues are going to the experimental site after coffee break or during the coffee break. So there is a possibility to go there to see the drones during the preparation. So for those of you who are going to the Friday's program, it has no sense to go there today, of course. The presentations are much better. But they were like 2 or 3 students requested me to take them to see the drones in action, because they are not able to be here on Friday. So if you are here, just tell me and we can take you there. If it's not the case, just let's continue with the presentation. So thank you, Antonio, very much for coming, and I am looking forward to see your presentations.
Thanks for the introduction and for the invitation. Okay, no problem. So my name is Antonio Franchi, and I am a permanent researcher at CNRS, which is the largest research institution of France. And it has many institutes located in all the main cities of France, and I am in an institute which is called the LAS, which stands for Laboratory of Analysis and Architectures of Systems, and in particular in a lab, in a department which is about robotics, and we work on robotics on from many different aspects, field robotics, humanoids, flying robots, human-robot interaction, and it's one of the largest robotics labs in France, and it's located in Toulouse, in the southwest of France. Okay, so my main topic of research are flying robots, control of flying robots, and also design of novel flying robots, and also control of multi-robot systems. And in particular, in this lecture today, I'm not going to talk a lot about flying robots, apart a few slides that you will see. But I'm going to talk, especially in this first part, about classical cooperative control of manipulators. My overall lecture, so the 2 parts, will be divided actually in 3 sections. The first section is rather classical. I want to give you a general introduction about modeling and control of manipulators that have to cooperate together to co-manipulate objects. And actually, this first part will be based on slides that have been prepared by a professor in Italy at the University of Basilicata, Fabrizio Caccavale. And so these are rather classic, so I don't know, maybe some of you will know, depending on what is your background, but I'm sure that many others don't know this. And in this part, I will also refer to many works in the bibliography, in the state of the art, so if you get interested into this topic, you have a lot of pointers here. Actually, one of the main entry points, I think, if you go in the handbook of robotics, the Springer handbook of robotics, there is an entire chapter devoted to cooperative manipulation. So I think this is a very good entry point. So at the end of this first part, I will, actually, let me go. So this is the outline of the first part. I will, at the very end, I will talk about what I consider the main challenges in this topic. So, in fact, as you will see from the citations, from the state of the art that you will see during this first presentation, many of the works have been done in the 90s, actually. So, cooperative manipulating systems for standard manipulators is an old problem which has been, let's say, solved in many ways. But there are new challenges now, and I think they are mainly related to bringing this kind of cooperative manipulation abilities outside of factories, outside of environments that are well known and well structured. And one example is actually the case of flying robots. So I will highlight this aspect. So this is the first part. It will be, as I said, rather basic and let's say academic, methodological. While in the other two parts, depending on the time I will have, I would like to show you two more particular problems that are more recent, are topics in which I worked in the last year. And in particular, in the first one, I will show you how to do cooperative manipulation using distributed algorithms. So algorithms in which there is not a single central unit that decides for all the manipulators what to do, but the robots have to understand about and let's say estimate online some quantities without full knowledge. I think it's a simplified setting, so these are manipulators on the ground and simple 2D, let's say, geometry. But there is the decentralized estimation and distributed control problem that is highlighted there. So this will be the second part. In the third part, instead, I will talk about cooperative transportation with flying robots and cables. And in particular, I will stress, also in this case, what are the fundamental aspects that allow cooperative transportation without using explicit communication. So again, this is something related to decentralization and distributed control, but in another setting. So the second part will be more on ground robots, and the last part, the third part, on flying robots. So maybe before I dive into the presentation, I would like to know among the audience how many of you are familiar with like nonlinear control or control of manipulators. Okay, how many of you know, for example, the model of a mechanical model of a manipulator of an arm? Okay, and how many of you are familiar with I don't know, what is a Lyapunov function, a Lyapunov stability? Okay. So you will see that especially in the last part, it will be rather theoretical. In the presentation, there will be also the proof of the theorems and so on. I will hand over the presentation at the end to the organizer, so maybe I won't have the time to go through all the steps, but they are there in the slides, and you can watch them later, and especially because I see that not many of you have all the tools that are needed to understand these proofs. So I think it's pointless to really, and there is also not the time to do it. But they are there. So you will see that in some slides they're very dense with the mathematical proofs. The reason why I put them is because to leave them in the slides for you to check later. Okay, so in this first part, I will first go through what is called the kinetostatics of cooperative systems, cooperative manipulation systems. You will see what is this about. Then I will quickly talk about the dynamics. And these two parts are about modeling of cooperative manipulators. Then I will give an overview of the main control methods used for cooperative manipulators. And in the last part, I will, as I already said, I will talk about current and future challenges, especially related to aerial co-manipulation. So why we, first of all, in first place, are interested in having cooperative manipulators? Why multiple manipulators? Is not one manipulator enough to do everything we need? And I think in your body, you have the answer. You have two manipulators in your body. So there is a reason why two manipulators are actually, at least two, more than one are very important. And to do some task, maybe sometimes you need even more, you need other people to help you. So you can increase a lot the tasks that you can do by adding more manipulators. You can do more complex things. So there is this joint multiple arm manipulation tasks that you can accomplish. Also, typically one manipulator has, by adding more manipulators, you can handle objects that are heavier, but not only, also objects that are oddly shaped or very long or large, for which to manipulate them, when I say so maybe it's very important to say at the beginning what I mean for manipulation and what is the difference between manipulation and transportation. So transportation is a basic task in which I just want to bring an object from point A to a point B. Typically not specifying what is the desired, only specifying what is the desired pose of the object. But for pose, I mean position and orientation. For manipulation, instead, I mean a process in which along all the action, across all the full action, the pose and the pose, so the position and orientation of the object have to be carefully controlled. For example, to avoid obstacles, or for example, to keep the object in a certain orientation. Otherwise, no. Let's say you want to, you have a glass of water and you want to bring it somewhere, and so of course you don't want to turn it upside down. Orientation is very important. And there are many other tasks in which orientation is important. So full control of position and orientation along the full trajectory, this is what I call manipulation. So it's precise control of the state of the object, while transportation is just bringing something from point A to a point B. Having more than one manipulator might increase what is called the dexterity, or the manipulability capabilities of the system. If you have an object that has, for example, you are taking an object that is long, and there might be some orientations for which you don't have enough strength to keep it in that orientation. While if you have two arms or more, you can achieve more dexterity. So you can manipulate the object in many more ways. So you can, in cooperative manipulation, you can differentiate between two main kind of tasks. One is a loose cooperation between manipulators, and one is a more tight cooperation. In a loose cooperation kind of task, typically only what is needed is just to coordinate the motion of the two or more robots, and there is no emphasis on the mechanical interaction. And this depends a lot on how the robots grasp the object. So if their grasp of the object is loose, then just by moving the two manipulators in a coordinated way, so that the two end effectors are not far away, too far away, and they are in a certain mutual orientation and position, it's enough to do the task. And while in the case, so for example, if two drones, let's say, handle an object through cables or a crane or something like this is a kind of loose coordination, loose cooperation. It's just enough that the two robots or more move in a coordinated way. Instead, a tight cooperation is when the manipulators grasp really the object in a more strong way, and in this way they influence each other in terms of a mechanical force and mechanical torques. So they need to, in this case the control is harder because also the forces have to be mastered, otherwise the object might break, the manipulators might break, or something can go wrong, or the gripper can lose the gripping of the object can fall down if the forces are too big. So in case of loose cooperation, what is very important mainly is the kinematics, while in the tight cooperation case, it's very important to also consider the statics and the exchange of forces. And there are the two manipulators. When you take many manipulators together, let's say the state space of the full system, it's typically the sum or the union of the state space of the manipulators. When they tightly manipulate an object, there are constraints that are introduced in the system, so their actual degrees of freedom are less. But this means because you have these constraints. Okay? And this means that the system is a closed chain. In that case, everything becomes more complex. The control, planning, because of these nonlinear constraints that appear in the differential equations. So it's not, it's much harder to plan and to control. I will not cover at all the planning problem in this talk. Okay, so let's start with the first important modeling part, which is called kinetostatics. You will see what this means. Kineto stands because it's about the kinematics, and statics because it's also about the forces exchanged statically between the manipulators. So let's consider this simplified setting, simplified in the sense that I will always talk about just two manipulators, but actually everything extends to more than two. You see them planar here, but actually you have to, I will not make the planar assumption. The equations are old for manipulators in 3D. So you have to focus your attention here on a few things. So there is a first frame, T, which is the word frame. It is an inertial and fixed frame. Then there are two frames attached to the two end effectors of the manipulators, T1 and T2, and they have their own orientation. And then there is a fourth frame, which is the object frame. This is fixed with the object to be manipulated, and is centered on a certain point of the object, which could be the center of mass or other points. And then there are this vector here, R1 and R2. They represent the position of what they are called in the literature the virtual sticks. You have to think that you extend the end effector with these virtual sticks that go into bring the end effector to this origin. They are like virtual sticks that pass to the object. And if the grasp is tight, they are basically the same. They constitute the same rigid body with with end effector. I forgot to mention, but if something is not clear, you feel free to, I mean, if you have questions that are really fundamental to understand or something is not clear in the notation and so on, please interrupt me. If you have questions that are more general or they extend the discussion with respect to what I am explaining here, keep it for the end. I will reserve up some part of the time for questions, more general questions. So far I think it's pretty standard and clear. So the manipulator has what is called direct kinematics equations. The direct kinematics, so let me go back here. So a manipulator is made by several links and joints. And these joints have typically 1 degree of freedom. They can rotate. And so you can describe the configuration of a manipulator by describing which are the angles of each joint. So if you know and let's say a manipulator has n joints, so if you know the angles of these n joints, that you know how the manipulator is configured, how it is, what is his posture. Typically, these joints variable are denoted in the literature with Q. So Qi is the vector of all the joint variables of the manipulator I. So you will have a Q1 and Q2. Given these variables, you have a function that tells you where is the end effector in space, in 3D. So this is called direct kinematics. So it's simply this. It's a nonlinear function of the joint variables that maps the joint variables, the joint angles, to the position of the end effector. Not only the position, but also the orientation, which can be represented in a matricial form as a rotation matrix. If you can use quaternions, other things, but I will use rotation matrix in this presentation. So this rotation matrix is also the function of, is actually a composition of many rotations. Okay? You can, but in the end, it's a rotation matrix. These are two nonlinear functions. Altogether, they represent the direct kinematics of the manipulators. And if you want to know what is the velocity of the end effector, so in order to, let's put it in this way, in order to control the position of the end effector and orientation, you need to move. Now, if you are in this position and you want to go somewhere else, you need to move. So what is important is actually to control the velocity, how it moves. If I am able to control how the end effector moves, I can bring it somewhere else. So this is why it's important to study how this moves. In a manipulator, what you can control are the velocities of the joints, and what we are interested in is what happens if I have some velocities in the joints to the velocity in the end effector. And the answer to this question is given by this equation, which is the direct differential kinematics, which shows that the velocities of the end effector of the joints Q dot map linearly with the velocity of the end effector. When I say velocity, I mean generalized velocity, in the sense that there is the velocity of the origin of this frame and the angular velocity of this frame. So this is a 6-dimensional vector that stacks the velocity of the position of the origin of the end effector frame and the angular velocity of the frame. And there is a linear relation between them, and the linear relation is established through this matrix J, which is super important element in control of manipulators, which is called the Jacobian of the manipulator. And it's not constant, because this is a nonlinear function which depends on Q. So when you differentiate it, you get a nonlinear matrix J. So it depends on the configuration of the robot. So this is a 6 by n matrix in general. Okay. So this is the direct kinematics. Then there is, in mechanics, an important principle which is called virtual work principle, which says that there is a clear duality between the velocity. So you can see, you can look at manipulator as a kind of mechanism that transforms velocities in input in velocities in outputs, like a gearbox does, let's say. It's like a complex gearbox in the end. You have a lot of joint velocities, that motors at the joint, and this transforms velocities at the end effector. Okay? And actually, this is the gearbox matrix. Okay? So you have a duality in terms of forces. So if you have a system that transforms this velocity from input to output velocity, then if you apply a force at the output, you will get some force being perceived at the input side. No? And the relation is given actually by, is also linear, and is again given by this matrix transposed. And this is called the statics of the manipulator, which is just enclosed in this equation that tells that the torques, so if you apply a force at the end and a torque at the end effector, and you call this force and torque as a 6-dimensional vector H, I again stands for the ith manipulator. Then at the joint level, the motors that are at the joints will feel a torque that is actually a linear combination of this vector H through the matrix that is just the transpose of the Jacobian that we have seen before. So just checking the dimension, this is so which dimension is this? Is n-dimensional. It's the dimension of the n joints. And this matrix, so is transpose, so is n by 6, and this is a 6-dimensional vector. Okay. So, and this holds only if everything is still. So if the manipulator is still, keeps everything still, and you apply force and a torque here, and everything remains in static, then these are the tau, are the torques that are perceived. Of course, if the manipulator moves, then there are all the inertial and centrifugal and many other terms that come into play. Depends how it moves. But so this is why it's called the statics. It's related to forces, but static forces. You will see the full model of the manipulator. So, but this will come into play. So every time, even if the manipulator moves, if something with interacts with the end effector of the manipulator, the result on how this maps to the joint level is given by this formula. What is the effect of this torque and force and torque applied at the end effector? Okay, so these are the two main equations for the kinematics, so this one, and the statics of each manipulator. Then you have what is called the object kinematics. So the object kinematics maps maps these two things. So now we went from the joint to the end effector, and from the end effector to the joint in forces. And now, and then we want to see what is the kinematics that maps forces and velocities at this point and this frame to forces and velocities in this frame. And this is the kinematics of the object. So the velocity vi is the vector of the is what you have seen before. So is this vi vector here. So this is related to the velocity of the frame of the object through another matrix, a simpler one, which is just this one, is a 6x6 matrix. And so I and O denote the identity and zero matrix. So this is a 3x3 identity matrix, just once and on the main diagonal. And O is just zeros. And minus S is the most complex matrix here, but it's still very, very simple. Is the matrix that is like representing the vector. If you multiply this matrix with any vector V, three-dimensional vector, it will give you the vector product with the vector R. R, I remember you, are these vectors here. So the displacement, the virtual state position vector. So S basically, when you see S times a vector, is a vector product. And why is there? I mean, if the object is rotating, the velocity of this point will be the vector product of the position of this point times the angular velocity. So this is why it's in this position, because V, the last three elements of V, of this V, this is again a six-dimensional vector, is the angular velocity. So the object moves. Let's go back here. So you have this object that moves, and this frame has a certain angular velocity and a certain translational velocity. The velocity of this point will be the sum of the translational velocity plus the vector product of this vector and its angular velocity. It's very simple, like this. And this is encoded by the first line, 3 lines of this matrix. And the second 3 lines are just mapping one-to-one the two angular velocities, because the object is rigid, so the two angular velocity completely match. So remember this matrix because we call it Wi. So again, there is a relation between two velocities. So remember, the Jacobian gives the relation between the velocities, angular velocities of the joints, and the velocities of the effector. And there is this matrix. And when you take the transpose, you have the relation between the torques of the joints and the torques and forces at the end effector. Similarly here, you can map, given that you have the map between the two velocities in the two frames, you can map what is a force and a torque applied in this point, how to map this here. Okay, you have the same kind of relation. And again, this mapping is given by the transpose. So we call this WT transpose. T stands for transpose. So we have to do the transpose of this matrix. When we do the transpose, since this is a skew-symmetric matrix, just the minus disappears. So we get this matrix. And these two vectors are exactly the force and torques applied by the end effectors by the end effectors on the object and by the external world on the center of the object. Yeah. So remember again this matrix W. This is called the partial grasp matrix. You will see. So maybe I spend a bit more time on this. So this matrix basically maps the force and torques applied by the manipulator on the object to, let's say, the total what the object feels in terms of force and torques in its frame, in its central frame. Why we are doing this? Because we are going to have multiple manipulators, and for each one there will be an equation like this. So the total force and torque that the object perceives or is subject to will be the sum of all these components. Okay? Then we know HI, how it relates to the torques by the manipulator, so we will compose these actions. And in order to do this, there are two main approaches. And the first one is called the symmetric formulations. And as you can see, it has been studied in the 90s, as I anticipated to you before. And there is another formulation which is called the task-oriented formulation to understand how to put together these pieces of information and to see how the manipulators influence the object motion and how the object motion in terms of exerted forces and how the forces from the external world on the object influence the manipulators. So let's first dive into the symmetric formulation. So, as I said, when you have two manipulators acting on the object, this manipulator will feel, this object will feel what I call an external force. It's the combination of the two forces, like generalized forces by the two manipulators, which is the sum of the two parts. And so you will have H1 and H2 sum together but passing through the partial grasp matrix. And when you stack aside these two matrices, you get the full grasp matrix. If you have more than two manipulators, you will just have many of these matrices altogether. So this is a very important matrix. So it has, in this case, in the case of two manipulators, its size is 6 by 12. But in general, it will be 6 times number of manipulators times 6. And why this grasp matrix is very important? Because these force and torques that are called the Hx are the ones that cause motion to the object. But actually, so if you look at the if you look at the dimensions, H is the set on force or torques that the end effector can provide. Is the vector of this, and this lives in a 12-dimensional space. So you can choose 12 variables by applying proper forces. But in the end, what will cause the motion of the object is only a 6-dimensional vector, because it's the total force and the total torque applied to the body. Total torque will make it rotate, a total force will make it translate, a combination of them you will have a kind of rototranslation. But in the end, it's only a 6-dimensional vector, while you can exert a 12-dimensional force and torque vector. So where the remaining 6 variables go into? So what do you think? Where do they go? They just disappear, or they cause something? Sorry? Doesn't move, yeah. So they don't produce motion. And if they don't produce motion, what they do? So we are two manipulators, we grab an object, and let's say the two end effector, they exert an HI, no? Each HI is just, so the torque, let's say, is 0, and the force is just in this direction for one manipulator and this direction, and they just cancel out, and they are of the same intensity. What you won't see any motion, so the Hx will be 0, but what will happen? Sorry? Yeah, there will be a stress in the object. So the remaining part of the forces are called what they are called internal force. They just result in a kind of stress or compression or extension of the object. If the object is rigid, you won't see any deformation. Nothing is really rigid, let's say, but if the stiffness of the object is very high, you will practically see no deformation. But there will be, so this will cause while if the object is flexible, you will actually see if the object is soft. So you really need to take into account this case. I'm mainly talking about rigid objects in this talk, so I won't talk about deformations caused by these internal forces. But the fact that they don't produce motion on the object doesn't mean you should ignore these internal forces, because you might break the system, not only if you grasp something and the manipulator, let's say, you need sometimes to, and you want to transport and manipulate something, you need sometimes to keep these internal forces in a certain set. You don't want them to be 0 because maybe the object could slip away or fall. You need, actually a very good example of I said that you have two cooperative arms in your body, but actually you have 12, let's say, because each of your hand is a cooperative manipulator. So a hand is an example of a cooperative manipulation thing. But the hand doesn't have a gripper in every finger. In order to keep the grasping, you need to have some internal force, otherwise the object will fall down. So when you do the cooperative manipulation with your fingers, you control the internal force. So how to define this internal force? So what is this internal force? A way to define it is the following. So this is the direct mapping between H, so the force and torques by the exerted by the two manipulators, into the force and torque vector that makes motion in the object. If we try to write the inverse map, so they'll say it will be undetermined because if we know this, we know 6 variables and we have to reconstruct 12 variables, so we don't have enough information. So what we will, but we can write down H as in part be constituted by this thing, I will explain what it is, which depends on the internal forces, and in part by the external forces, and in part by the internal forces. So forget for a moment that this is about forces and torques. Just look at it in an algebraic way, linear algebra. So you have a vector, 6-dimensional vector, a 6×2 matrix, and a 12-dimensional vector. You want to invert this equation. So you can write H as the pseudo-inverse of W times this vector, plus, but this doesn't represent all the solution of the linear system. You can add any other vector that is in the null space of W. In fact, if you decompose H in 2 parts, one that is in the null space of W and one which is not, when you multiply with W, only the part which is not in the null space will contribute to the generation of H. The rest is completely arbitrary. And how to represent this? We represent this by taking a matrix which has as columns a basis of the null space of W, and we just take any linear combination of these 6 columns. Is it, so how many of you need a more deep explanation of this part? Because is it clear, the null space? It's clear? Please stop me if it's not clear. So you have in the end that this matrix is a 12×6 matrix, the pseudo-inverse. So the columns of this matrix represent the direction of H, which cause a motion of the object, while the columns of and they are mapped through a linear combination whose coefficients are the one in H, external H, while this matrix V has columns, a basis of the null space of W. So whatever linear combination you take of the columns of V, they won't result in any motion of the object, but they will result in compression or extension or pressure on the object, and these are the internal forces. So if you put together these two matrices, W pseudo-inverse and V, you get a matrix U, which is full rank. So which size is U? U transpose. What are the dimensions? in your opinion? Speak loud. 12 by 12. So this is a square matrix, and it's full rank because it's designed in that way. I mean, this is a this because of the fundamental algebra theorem. Because the two spaces that are in the column spaces of these two matrices are in direct sum. This is the technical term. And so this matrix is a square and full rank, so it represents a change of basis in the space of H, and the change of basis which separates the torque and forces that the end effector can exert in two parts. A part which provides motion and a part which provides internal forces. Okay? Okay, so how does it look, the pseudo-inverse of the grasp matrix? It looks like this for two manipulators. So it can be computed in a closed form. It's pretty simple. And also so how does it look V? The choice of V is not unique. You can have many bases of the orthogonal bases of the null space. So this is a possible choice, for example. Okay. So in terms of sets, just to again stress what is the role and meaning of each matrix and vector here, you have to think that you have the space of the manipulator where the manipulators live, which is the space of H, in which the force and torques of exerted by each manipulator are defined, and it's a 12-dimensional space. And so through the grasp matrix W, 6 by 12 matrix, they are mapped into the force and torques that generate motion on the object. And so the image space of W generates Hx. And all the forces and torques that cannot be generated to the grasp matrix, they map back into the null space of W through the matrix V. So now we defined this mapping here. So, and this is a mapping between, it's a static mapping between force and torques of the object and force and torques of the manipulators. We can use this virtual world principle in order to write down what is instead the velocity mapping. So we just have to take the transpose of the previous matrix. No? You remember U is W pseudo-inverse V. We just make the transpose. And this maps the velocities of the two end effectors with the velocities of the so Vx is really the velocity of the frame, and Vint are the internal velocities. But these internal velocities, if the object is rigid, must be 0. So from this equation, setting the internal velocity to 0, we have this important constraint. So that the velocity of the end effectors, V, this is the stack of V1 and V2, must be in the null space of big V transpose. And this really, it's a constraint. So once the manipulators have grasped the object, the velocity cannot go outside of the null space of this matrix. You can also recast this as a velocity of the joints by just replacing V with the Jacobian times the Q dot. It means that once the two manipulators have grasped the object, their joint velocities must be coordinated. You are imposing constraints on them. This is the kinematic, the closed chain, basically. Okay. I skipped this for the sake of time. So this is called the symmetric formulation. Is good for, I mean, it's completely describing the kinetostatics of two manipulators manipulating an object. These are so the one I showed you are the important equation where to start from. Whatever you want to do with a group of manipulators cooperatively handling an object, these are the equations you have to start from. And then, depending on your particular problem, you instantiate your particular problem. Okay. So these kind of variables are sometimes not really handy in order for some control tasks. Because they cannot really geometrically being interpreted very nicely. So there is another representation which is equivalent, which is called the task-oriented formulation. And instead of talking about like the position of the two manipulators separately, and an orientation of the two manipulators and the forces exerted by the two manipulators, they separate in this formulation, the motion variables are separated in absolute and relative. So how the manipulators move in absolute way altogether, and how they move internally with respect to each other. Okay, so this is the difference between absolute and relative. And so you do kind of a coordinate transformation from the position of the two manipulators, P1 and P2, you move to PA and PR, where PA is just the average of the two positions. So you have to, let me go to this picture. So these are the two manipulators' frames, this one and this one. You just take the middle point, and the position of this point, this is PA. Okay? And then you take the middle rotation. So this is oriented in a certain way, and this is oriented in another way. You just define, so when you have two frames, you want to go from this frame to this frame, it's just one rotation, of course. And this rotation can be represented as a rotation about one axis of a certain amount. You just define this axis, and you rotate by half of the amount that is needed to go to the second frame. And this is defined as RA. So it's like half, this is why there is a half of the rotation needed to go there. And then you will end up in an intermediate frame, and you consider the orientation of this intermediate frame, and this represents the absolute orientation of the two manipulators. It's somehow an average, a way to define an average orientation between the two manipulators. And also like you have an average position. So if you know where this position is and how this orientation is, you know in average how the two manipulators are positioned. But you don't know where they are with respect to each other. In order to reconstruct also this, you just take the difference between the two positions and the relative orientation between them. So it's just a change of coordinates, the rotation from one to the other. So you have these absolute and relative frames. So we define the position and the rotation matrices. Now, if we have to go to the kinematics, we define the velocities. So this is just the average of the velocities, and also the angular velocity is the average between the two angular velocities. And again, for the absolute part and for the relative part, you just get the differences. It's a transformation between two velocities, two sets of velocities. So again, there is a kind of Jacobian that maps the two. You can rewrite these equations in a matricial form. This is just a way to rewrite these equations. And this represents the Jacobian between the two transformations. And you can call this matrix T. And then, since we already defined the kinetostatics for V1 and V2, if we want to know them for the VA and VR, we just apply composition. So in terms of forces, now here you have T, you need to use T transpose again for this virtual work principle. And also for, in the end, for given that you know V0 and you want to go, or you know Vt and you want to go to V0, you have this, you have the composition of U and T. And if you have, this is invertible, this T. And so if you want to know from Vt, for V1, V2, you just invert this matrix T. So this is why here there is the inverse. And if you want to go from the HO, which was the representation of these external internal forces, generalized forces, into the kind of the HT, which somehow represents the generalized forces that cause the whole system to move and rotate, so the two manipulators together, or the two manipulators to move with respect to each other or to rotate with respect to each other. And then you just use this transformation. Okay. Let me see, because it's already 10. I have to finish at 10:30, right? This is the schedule. Yeah. So I want to also talk a bit about control, so I skip this part. So let's talk about the dynamics. So far we talked about kinematics and static forces and torques. Okay, this was the kinetostatics. When we go to dynamics, what we, in order to fully describe the motion of a manipulator, it's a mechanical system, you cannot stop at the kinematic level. You need to, because forces and torques applied to the system, what they change directly are the accelerations related to the body, the multi-body system. So we need to consider the dynamics equation of it. These dynamics equations have to be written for at least three, let's say there are three actors. The two manipulators and the object. Each one separately has its own dynamics. But they have to be, so we can have a dynamic model for the manipulator, the dynamic model for the object. But there is the closed chain kinematic constraints that we have seen before that will link the two together. So the dynamic model of the manipulator in the joint space is this one. For the ones of you that are not familiar with this equation, I will just go through the meaning of each part of it. Any mechanical system that is defined by Lagrangian coordinates can be then put in this formulation. So M of Q is the inertial matrix, so it's an n by n matrix, which is a positive definite, symmetric, and depends on Q. Q double dot, of course, is the acceleration, the angular acceleration of each joint, the stack of the angular accelerations of each joint. So this is a n by n matrix times an n-dimensional vector. So this part is a nonlinear function of that depends on Q and Q dot, and includes all the centrifugal Coriolis terms. And actually, you can prove that this part is linear with respect to Q dot. But where the matrix that makes it linear depends again on Q and Q dot. And then on the right, you have two components. One is the torques applied, which is an n-dimensional vector of the torques applied to each joint, tau. And one, so you should now get familiar with this, is the effect on the joints of external forces and torques applied on the end effector, which is this vector, which is mapped through the transpose of the Jacobian. and there is a minus in front of it because this is the, before we were seeing how the torques, if I apply some torques at the, I mean statics, at the joints, which external force I will produce on the end effector, and this is the converse. So how the external forces on the end effector affect the dynamics of the system. So this is very standard. The dynamic model of the manipulated object is just, can be just written using Euler, also Newton-Euler equation. So they look pretty similar. So there is an inertia matrix, and this is the acceleration caused by the external forces, so the external acceleration. Again, external means what causes the motion. Okay? So here you will see the linear acceleration and the angular acceleration. This is the velocity and the gravity, because it's subject to gravity. I forgot to mention that in this vector here, also gravity is included. And gravity depends on Q. If the manipulator is like this, or completely vertical, you will feel a certain gravity force on the joint, but if the manipulator is like this, the joint will feel the gravity in a completely different way. And then you have the closed kinematic constraints. So if we put together all these things, we have manipulators, and these H are the external forces applied on the end effector, the object, and these are the external forces applied on the object, and we know that these two things have to somehow match, but the way they match is through the grasp matrix. Okay? So we can replace one of the two, we can replace Hx by Wh, so that is fully connected, and there is this constraint. This constraint which has to be satisfied at all times. So there are ways to incorporate, embed this constraint into the equations, because in the end you have n1 plus n2 variables, but they are not all free, because you have these 6 constraints. So you have to be sure that they live on a manifold, and so the dynamics will have to be integrated, for example, if you simulate the system or you control the system on this manifold. When you want to, so I don't know whether you are familiar with, in the case of a single manipulator, there is a concept which is called manipulability. I didn't prepare proper slides for this concept, but actually it tells you how dexterous is a manipulator in a certain configuration. You can understand this in an anthropomorphic way. So if you look, for example, at your, I'll give you an example, where your mouth is located with respect to your hands, you will see that when your hand goes in your mouth, the arm is in this position, and this is not at all random. The mouth is not here, it's not here. You don't have to feed the mouth here and here, it's really here. Why? Because in this place, your arms are in the maximum manipulability configuration. They can go in any direction very easily. If your arm is stretched like this, and you have to go more in this direction, just with the arm you cannot do it, you have to move the body. Okay? While if I'm here, I go in any direction and I can turn in any way here. So the manipulability tells you what is the capability of motion in the different directions given a certain posture. And you can, basically you have to look at the Jacobian, and there are some indexes that are related to the Jacobian. It could be related to the singular values of the Jacobian, to the other, the condition number, or these kind of things. Okay? And there is a concept which is called manipulability ellipsoid, which tells you in which direction you can move more easily, and in which direction you can move with less easily. So this ellipsoid will have a long axis in the direction in which you can move easily, and small short axis in the direction in which you cannot move easily. And of course, what you want typically is that this ellipsoid looks as much as possible as a sphere, so that you have a full manipulability. So there are similar concepts in cooperative manipulation cases. So assume first of all, there is a dual concept, which is the force ellipsoid. So there are directions in which you can exert a lot of force and directions in which you cannot exert a lot of force. And actually, this is dual with respect to the velocity manipulability. If you have to resist to somebody that pushes you, you won't stay like this typically. You try to stay like this, really fully stretched, because in this way your structure will give more strength to you to resist. So if you have to resist a force and you are here in this position, you have to use your muscles, your joint torques to resist. While if you are like this and you press me, my muscles, I mean, I don't use the muscles of my arm actually, only the muscles of my body, because the structure prevents the motion, the compression of my arm. So if the force is such that it doesn't destroy my arm, I can withstand it. Okay? So, but you remember that this direction is actually the worst direction in terms of velocity. So the worst direction in terms of the velocity is actually the best in terms of force. There is this kind of duality. So by putting two manipulators together, you can have that in one direction, one manipulator helps being strong, and in the other directions, where one manipulator is weak, the other manipulator can help. So you can compose these manipulabilities together and get better manipulability properties. Okay. Okay, then so if you don't, do you have questions regarding this first modeling part so far? I mean, if you have really questions about the slides. If you have other questions, curiosity, let's leave it for later. So regarding I will talk now a bit about control. The early approaches about cooperative manipulation control were based on what is called this master-slave or leader-follower approaches. The idea was that you have one manipulator that is like the master, and it has a force sensor, and this manipulator, and the slave has a force sensor. The master has is just rigidly attached to the object and moves the object like if it was a single manipulator. And then there is a second manipulator which has a force sensor, so it can be compliant to the motion of the other and just help the other. It's like if they don't really cooperate together. It's just the second manipulator that helps the first one. This was the very beginning of it. I think it was in the 70s. Dates back to the 70s. But of course, this is not an optimal way to do things. So then there were many other methods that were based on approaches that are not master-slave based. And these are the four main approaches. One is what is called hybrid force control. The other one is model-based feedback linearization control. And the third one is impedance control. And then there is also these are also these kind of methods which I won't describe them, but there are the references in the slides. So in standard approach, what you assume is that you have force sensors in every manipulator. So you can feel the force and you can control it. So hybrid control, how does hybrid control works? In order to understand hybrid force control, you have to think what you do, for example, when you write. When you write, you have an hybrid task that you are doing. You want to move, but you also want to press. Keep pressing. So, and what the properties of these two actions or these two tasks? The main property is that they are orthogonal. You want to move on the sheet of paper and you want to press in the other direction. So you see the force task, so the pressure is in one direction, the motion is on the plane that is orthogonal to this direction. So this is the concept of, this really is the basis of hybrid control. You define some directions in which you want to do a force task, and other direction in which you want to do a motion task. And for many practical tasks in real life, this is really what you typically do. And so in order to do this properly, typically you need to be, you know, if you want to follow very well a trajectory in motion, you need to be very stiff. You need to be there whatever the external disturbance affects your motion. But in order instead to do a force control task, being too stiff is not a good idea. You need to be compliant because you never know whether the environment is stiffer than you or reacts in oscillates and so on and so forth. So the idea of hybrid control is to decompose the space in this orthogonal. So the example I made was only for force in three-dimensional, but you can extend this, of course, to torques as well. For example, assume that you want to do peg in all task. Then you have to be typically compliant about in this motion, and maybe not compliant in this direction, in this, because you don't want to turn like this. You want to peg, you want to put the peg in the hole, and so on and so forth. So the idea of this kind of control, which is summarized in this kind of scheme, is that you have your ARM system. These are the two important matrices, S and I minus X. S is the matrix that selects the components of the motion and of the force. It's a selector matrix. And I minus S is like the complementary of it. So the components that are selected by S are not selected by S, are selected by I minus S. So the loop on the top controls the position, given a desired position, and the loop on the bottom controls the force and torques, given a desired force and torque. Here you see that you have the Jacobian transpose that plays a role because you map the desired force and torque to desired force and torques applied to the manipulator, to the torques, to the joint variables of the manipulators. While here you have the Jacobian inverted, the inverse of the Jacobian, because you want to go from, you have the kinematic, the kinematics of the robot, and you invert the kinematics of in order to go from a desired motion of the end effector to commanded motion of the joint space. And apart from, and then you have some gains, depending if you implement a kind of proportional derivative controller or integral controller, depending on what you implement, you will have a certain transfer function of the control. So this is pretty standard. Then given that you have these two, so these two torques, the generalized forces that to be applied by the manipulators will be just summed together. You know that they are going to be orthogonal, so you just sum together and you mix them, okay? Instead, in a model-based control that, assuming that you know very well all the manipulator models, you know very well the inertia matrix, each term, so, and the gravity compensation, the gravity term, and so on and so forth. If you apply this kind of control, so let's go back to the model. Because I think, so take this model, okay? If I apply a control in which I multiply M by something, I will, and I apply also N here. n, basically I cancel out these terms, and then whatever I put here will be the dynamics of the acceleration. So this is called the feedback linearization. And then so basically I completely cancel the nonlinear terms of the manipulator. The manipulator becomes, the end effector becomes like a fully controlled object in 6D, okay, in rotation, translation and rotation, and I do force control on it. So here, and in particular, I can control the internal force. This is just a PI controller. So the motion is controlled in this way, and then I control the internal forces. Because even if I control the motion of the two manipulators, there might be some discrepancies. And if I don't take under control the internal forces, as I said before, you can break the whole thing. Okay. So this is just, this still means is the error between the desired internal force and the current one. And they will follow a certain dynamics, in this case a PI dynamics, so you will eventually go to the desired internal force. Then actually the third kind of control is called impedance control, and I would say is the most used and the most effective one. So if you have to learn one of the three controllers that I described here about cooperative manipulation, learn the impedance control. What is the overall idea? The idea is that you don't try to exactly bring the system in a certain position and exactly having a certain force exerted on the object. But you mostly, so what you try to do, define by, or to let the control define, or is to let the system behave like a second order mass spring damper system with certain values for its stiffness, its damping ratio, damping factor, and its mass. And then, depending on what the external world will do on this, on the object will move accordingly to this model. So you don't know whether the system will go to a certain position or not, but you know that if no force is exerted on the object, not from the external world, not from the manipulators, the object will go in the position you want. But if there is an external force, it will move, and it will, the displacement will be kind of proportional with respect to the intensity of the external force that is applied. And you know that if a force is applied, it will start to move very slowly if you want to mimic a very big mass, or very, very fast immediately if you are mimicking a small mass, or and so on and so forth. And so how do you do this? You do this if you can measure acceleration, velocity, and position of the object. You can let the system have this kind of form, okay? Where this is the mass that you want, the damping, and the stiffness, and these are the external forces applied to the system. So this is for the manipulators, and this is for the object. If you instead, so the main problem typically with this so with impedance control is that you need to know the acceleration of the object, and typically it's hard to know it precisely. And so if you are okay to keep the same mass, the same inertial properties of the object itself, then you can avoid to measure this acceleration, but you cannot shape the inertia of the system. So in the end, the control looks like this. You have your manipulators, and you have a motion controller inside. Then there is a first loop, so this is the first internal loop. And then you have a second loop which shapes the impedance. So it measures the external torques and forces that cause stress, and decides the motion accordingly to mimic a certain dynamics. And then you have the impedance layer on the object, on the external forces of the object. Given the time and also the fact that I knew that the audience is a bit scattered here, I didn't want to go exactly on the equations that define this system, but I have some videos that show this approach. Let me see whether the sound. I didn't know that the sound was. I can change. This is. Yeah, it's not needed the sound. So this is in this video from the group in Naples that is mentioned here. This is a video from 2008. You can see that there are two manipulators and an object, and if there is no external force, so the two manipulators have a force torque sensors. If there are no external forces, the object is just kept in the desired position. But as soon as there is some external force or some external torque, the object moves and the manipulators moves accordingly, but they always keep enough internal force to squeeze the object and to keep it. And and the damping and the stiffness are completely different depending on the axis. You have seen before that the object was rotated, and then the manipulators really almost didn't go back to the initial position, because probably the stiffness around, we'll put back the video, yeah. The stiffness about this axis, rotational axis, is very small. While in other direction, the manipulators were putting back the object immediately. So the stiffness is higher. So this is really impedance control in cooperative manipulation is really the way that is commonly used, because it provides also safety and compliance, and you can shape all these properties. And also an amazing example that was displayed at DLR back in 2008, the time I was doing my PhD, is this Justin robot, which has two manipulators that, thanks to this kind of impedance control scheme, that you can have, this is a kind of virtual spring that defines the internal forces. You can have this kind of task, cooperative manipulation tasks. So in this case, everything works very well, because these arms so the model of these arms was perfectly known. This was built, these were arms built by DLR. The sensor used are top-level sensors, top-level motors, and so on and so forth. So you can achieve this kind of behaviors. Okay, so time, I think, of the first part is over. I had the last part of this, which is about going toward the flying manipulation, but I will keep it for the next. Yeah. So we will also the questions will be kept for the next part then. Okay.
So do you prefer to leave the question for the next, or
we can have questions for this part so far.
Yes. So please, if you have questions for Antonio for now, it would be maybe better to ask now for this part. Otherwise, we will forget everything, And for the next, after the next part, you can ask again for the next part. So please, do you have questions?
Yeah.
Right.
Hey, thanks for the talk. It was really great. The part about the manipulability ellipsoids, where you're talking about how controllable the arms are in particular configurations.
I don't hear you very well. Can you?
Oh, sure.
Yeah.
Is this a little better?
It's okay. It's just that there are a lot of low frequencies. But can you hear well?
Okay, I'll try.
Try. I will try to understand. Yeah.
Okay. So when you're talking about the manipulability ellipsoids and the force ellipsoids, are they strictly diopposed? So are there configurations where you're also maximizing your manipulability as well as the force that you can exert?
So I didn't get completely the question. So are they strictly opposed? So you typically, the opposed configuration is only, opposed you mean that they face each other? No, it's better without mics. It's perfect. Yeah. Yes, I see what you mean. So using one manipulator alone, typically you cannot maximize both because they are inverted. But the fact that you can use two, so maybe one can be put in a configuration in which it has not a lot of velocity manipulability, but a lot of force manipulability. And so the fact that you use two or more makes it possible to maximize all of them at the same time. So this opposition between having one thing or another thing goes away. This is the strength of this. For example, I think like tennis players, there are some of them that like to use two hands. I think it's related to this, that they somehow maximize. With one hand, maybe you have a good velocity, but not force or not precision, and something must be related to. So motion is related to precision, accuracy of the motion. In some direction, you are very accurate, but not very powerful. And in other direction, you are powerful, but not very accurate. And by using two manipulators or more, you can achieve both of the objectives, yes. So they are not anymore, to answer your question, they are not anymore opposed when you, or I would not say opposed, they are not anymore, it's possible to achieve both objectives at the same time, while for a single manipulator is not. Yes. Without mic, yeah, I think it's better. Yeah. Mm-hmm.
Object because it's uniform. But what happens if the object is a really random object which you don't know where the center of gravity is?
Yes. So yeah, it's a very good question. First of all, in the formulation I presented, the point C is not necessarily the center of gravity. So it can be any point. So the center of gravity can be anywhere. But the center of gravity plays a role because in the dynamic equations, you need to know where the center of gravity is in order to write them properly. So, for example, in the end, this point is not can be any point, not the center of gravity necessarily, but to write down the dynamic equation, you need to know where the center of gravity is. So it's true that if you don't know where it is, you need to estimate where it is in order to apply the control law. Yes, there are works in which they try to estimate all the inertial properties of objects. So a manipulator takes an object and then shakes it and does something, and then you understand where is the center of gravity. And actually, this is related to the second part of my talk, in which I will show you that you can actually estimate the position of the center of gravity in a distributed way with a group of manipulators. Yeah. Please. So you want to know how to whether it is possible to use another channel in the operational space. Yes, in the Yes. So I skipped this part, but of course there is a whole bunch of works which do the cooperative manipulation in the operational space. And so yes, you can, and you have to look in the works mainly by Khatib, Oussama Khatib, and he really worked in the 90s on cooperative manipulation in the operational space. So you can transform them to all them tools and matrices that are needed for the operational space part. Yeah. Yes. Yeah. Yes, you can. Yeah. So the difference between the two, so in one case you need, in the case of impedance control, you need to know very well the model of your robot, and so be extremely sure that the torques you apply will have the effect you want. But typically you don't always need a force sensor. Okay, this is the advantage. While if you go in the admittance paradigm, the force control part doesn't know much about the manipulator, and you assume there is a very good position control or motion control of the manipulator that is already available and you buy the manipulator and it's very good in controlling its position, and you but you need to measure the force. So depending on the robot you have, if it is a very accurate robot to move and very strong, then it's an admittance paradigm is very good. But if it's not a robot that can control the position very well, or is a robot of which you know very well the model, then an impedance control is perhaps better.
Another question?
Yes. 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 Yeah, you can adjust them online. So the question is whether they can be adjusted online and how to choose them also. How to choose them. How to choose them depends on the task. So if you remember, one of the first approaches is is disturbing the video going in background, or is okay for you? Okay. One of the approaches called this hybrid force motion control, and I think it's a good. If you start from this, if you assume you want to do an hybrid task, but you implement it with an impedance approach, you have a good initial guess of how you want to tune your stiffness and damping in this way. In the direction in which you want to do more motion control, you put a very high stiffness, because in this way the system will be less sensitive to external forces and will go where you prescribe the system to go. And in the direction in which you want to do more force control, you can lower the stiffness. And you prescribe a motion of the system that is such that you will have a certain internal force. So let's say I want to push and I make an example. So I want to push and slide. So if I use an impedance an hybrid force control approach, it's easy. I mean, it's easy. It's clear what I have to do. Control the force in this direction, control the motion in this direction. And the hybrid force control approach does it. If I want to use an impedance control approach, I have to define a desired position for my finger tip, but I have to shape the stiffness and the damping and the mass for in all the direction. So in this, what I will do is that, first of all, the position cannot be given exactly as the surface, as the position of the desired, let's say the line I have to draw. Otherwise, I will always have almost zero force contact with the environment, which is very brittle. Any external force applied that will make the robot go up will let the robot lose the contact. So in order to have always a pressing force, you need to have that the desired position is inside the object, a bit inside the object. And then you define your stiffness such that, let's say the displacement, how much is the desired position inside the object, times the stiffness makes more or less the force that you would like to push with. So this gives you a hint about how to design the stiffness in this way. And on the other direction, you make a very strong stiffness such that you really follow well the position. So these are some hints. Then, of course, then you have to see the damping, but it depends on the task and the properties also of the system you want to interact with. I hope it replies to your question.
Thank you, Antonio, for the first part. Now let's refresh with coffee and some cakes, and we will continue in 10 minutes. So please be here in 10 minutes, so it means 10:55. We are starting.